Here is an AP Chemistry energy problem way back from 1974 in the form of a free response question. Let's go ahead and solve it. We've got some tungsten 6 oxide being hydrogenated to give elemental tungsten and water. And they say the following tungsten is obtained commercially when you reduced the WO3 tungsten oxide with hydrogen according to the equation above. The following data related to this reaction are available. We've got the heats of formation for some reactants as well as some products. If you'll take a look at this, both of these are elements in their most stable form, so we don't need those to do table calculations. We've got some free energy numbers as well. And they want to know the value of the equilibrium constant, K. Well, what do we have for K? We have delta G equals minus RT times the natural log of K. However, standard conditions, so 25, we do have temperature. We can figure out delta G for the process, and I think we could solve it that way. We will do K equals E to the whatever in order to solve that. They want the change in entropy. That shouldn't be a problem because once we have enthalpy and free energy, we can use delta G equals delta H minus T delta S to solve for S. And finally, they want the temperature at which the reaction is in equilibrium at 1 atmosphere. So for that one, we'll solve it for T and make G equal to 0, delta G, because that's the number it needs to be at equilibrium. Let's see how we did. Okay, we start by finding products minus reactants to get the change in free energy. Don't forget to multiply the coefficients. So 3 times that number minus, ignore that, it's just elemental, minus 1 times that number. And there it is, and we get a value for the change in free energy. We can now find K by plugging into that rearranged formula. And here is our value for K, and it's very, very low. That's A, it's done. Part B, this will just be not products minus reactants. We don't have that entropy data, but we do have delta G equals delta H minus T delta S. Here it is rearranged. That is handy. Plugging in, we find that we have a change in free entropy of positive number. Things are getting more random. And finally, for the temperature, T equals delta H minus delta H over delta S when delta G equals 0. And so we go ahead and turn those over. So at 938 Kelvin, this reaction is in equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. This is an AP chemistry problem dealing with energy from 1974.